So, good evening, everyone. My name is Mehak Jain. I am a BTech Computer Science student of Acropolis Institute of Technology and Research, Indore, and the topic which I explained today is virtual memory. So, virtual memory expanding your system horizons. This presentation explores virtual memory. Virtual memory makes the computer feel like it is having the unlimited RAM. We will cover its core concepts and benefit. Finally, we will dive into its mechanism and impact. So, virtual memory. Virtual memory is an important feature of operating system which produces a kind of illusion that I have a large amount of memory. So, virtual memory lets processes run even if they exceed physical RAM. It creates an illusion of a large continuous address space for each process. This technique separates logical and physical memory. In other words, virtual memory is a storage scheme that provides user an illusion of having a very big main memory. This is done by treating a part of secondary memory as the main memory. Virtual memory is implemented using demand paging or demand segmentation. Instead of loading one big process in the main memory, the operating system loads the different part of more than one process in the main memory. History of virtual memory. So the concept of virtual memory emerged in the late 1950s and early 1960s, a pivotal innovation to overcome the limitation of physical memory in early computing systems. Pioneering work at institutions like the University of Manchester and MIT led to its practical implementation, allowing programs to exceed the physical RAM size and improving system utilization. The first system to fully implement virtual memory was the Atlas computer in 1962, followed by widespread adoption in mainframe systems and later in personal computers, fundamentally changing how operating systems manage memory. Virtual memory fundamentals. Virtual memory relies on several fundamental concepts to create the illusion of vast memory and manage physical RAM efficiently. Virtual address space. Each process is assigned its own private virtual address space, a large range of addresses that are independent of physical memory. This allows processes to operate as if they have exclusive access to a large contiguous block of memory. Page table. The operating system maintains a page table for each process. This table maps virtual page number to physical frame numbers. When a process accesses a virtual address, the hardware translates it into a physical address using this page table. Paging. The virtual address space and physical memory are divided into fixed size blocks. Virtual memory blocks are called pages and the physical memory blocks are called frames. These blocks are typically 4 KB in size. The pages and the blocks are of equal size. Swapping. Paging to disk. If a required page is not in physical memory RAM, it is loaded from the secondary storage like an SSD or SDD into an available physical frame. Conversely, less frequently used page in RAM can be moved back to disk to free up space for more active pages. Concepts in virtual memory. Virtual address space. Addresses generated by the CPU. These are logical addresses used by programs. Physical address space. Actual RAM addresses. This is the real memory hardware. Memory Management Unit MMU hardware translating virtual to physical address. It is crucial for memory protection. Pages and frames. Pages are fixed size virtual memory blocks. Frames are corresponding physical memory blocks. Demand paging. Virtual memory is implemented by using a technique which are called demand paging or demand segmentation. Page fault. If CPU demands a page which is not present in the main memory, then page fault occur. So a virtual memory is a memory management technique used by operating system to give the appearance of a large continuous block of memory to applications, even if the physical memory RAM is limited. It allows larger application to run on system with less RAM. So how virtual memory works? Virtual memory creates the illusion of more physical memory than it actual available, enabling program to run even if they exceed RAM capacity. This is primarily achieved through a technique called demand paging. CPU generates virtual address. The CPU issues a virtual address for data or instructions. This address is logical and independent of physical memory location. Memory Management Unit translation. The Memory Management Unit MMU intercepts the virtual address and attempts to translate it into a physical address using the process page table. Page fault occurs if the required virtual page is not currently in physical RAM. A page fault. The MMU cannot complete the translation. This triggers an interrupt to the operating system. Page loaded from disk. The operating system identifies the missing page on secondary storage, such that SSD SDD, find a free frame in physical RAM and load the page into it. Page table updated. The page table is updated to reflect the new physical address mapping. The interrupted process then resumes execution as if no delay occurred. This demand-driven approach means pages are only loaded into RAM when they are actually needed, optimizing memory uses and allowing larger programs to run. Type of virtual memory. Virtual memory can be implemented using different techniques to manage how data is swapped between main memory and secondary storage. The two primary methods are demand paging and demand segmentation. Demand paging. This technique loads fixed size blocks into memory only when they are needed. It is the most common implementation of virtual memory due to its efficiency and simplicity. Demand segmentation. Similar to demand paging, but it loads segments, variable size logical blocks into memory as needed. While less common in modern systems, it offers a logical view of memory aligned with program structure. Benefits of virtual memory. The main objective of virtual memory is to support multi-programming. The main advantage that virtual memory provides is a running process does not need to be entirely in memory. Larger programs run programs bigger than physical memory. Programs can be larger than the available physical memory. Virtual memory provides an abstraction of main memory, eliminating concern about storage limitations. Higher utilization. Increased multi-programming boosts CPU use. Enhanced protection. simplified management and memory protection, reduce crashes, processes are isolated, preventing memory errors, memory use, more efficient use of memory. Next is demand paging. So demand paging is basically a technique through which we implement the virtual memory. Demand paging is a technique used in virtual memory systems where the page enters the main memory only when requested or needed by the CPU. In demand paging, the operating system loads only the necessary pages of a program into memory at runtime. Instead of loading the entire program into the memory at the start, a page fault occurred when the program needed to access a page that is not currently in memory. The operating system then loads the required pages from the disk into memory and updates the page table accordingly. This process is transparent to the running program and it continues to run as if the page had always been in memory. There are two types of demand paging. First one is normal demand paging and second one is pure demand paging. In normal demand paging, some pages are in the main memory. So replacing is happen when page fault service required. And in pure demand paging, all the pages are in the hard disk. There is no page in the main memory. When page required, then the page come into the main memory. Demand paging, loading on demand. Page not in memory. A process try to access a page not currently in RAM, causing a page fault. OS handles fault. The operating system intervenes, find a free frame and load the required page from disk. Update page table. The OS updates the page table with the new frame mapping and the process resumes. Replacement algorithm. If memory is full, page replacement algorithm like LRU choose a page to evict. Page fault. The term page miss or page fault refers to a situation where a reference page is not found in the main memory. Or we say that if CPU demands a page which is not present in the main memory is called page fault, or we can say that page fault occur. In case of page fault, operating system bring the faulted page from secondary memory to main memory by replacing a page which is not needed and update the page table, known as page fault service. When a program tries to access a page or fixed size block of memory that is not currently loaded in physical memory RAM, an exception known as a page fault happens. Before enabling the program to access a page that is required, the operating system must bring it into memory from secondary storage such as hard drive in order to handle a page fault. In modern operating systems, page faults are a common component of virtual memory management. By enabling program to operate with more data than can fit in physical memory at once, they enable the efficient use of physical memory. The operating system is responsible for coordinating the transfer of data between physical memory and secondary storage as needed. As fast to do the page fault service, there must be less EMAT, that is effective memory access time. In case when page is already put in register, then EMAT, that is effective memory access time, is TMM. Or if the page in the main memory, then EMAT is equal to twice of 2mm. Page replacement techniques. When main memory is full, the operating system must decide which page have to remove. This technique ensures optimal system performance by managing memory efficiently. Page replacement techniques name. First one is FIFO, that is first in, first out. Evict the page loaded earliest, simple to implement but can be inefficient. Second one is LRU, least recently used. Removes the page unused for the longest time, offer good performance by predicting future use. Optimal algorithm. Evict the page not needed for the longest future time. It is ideal for benchmark but impractical in real systems. LFU, that is least frequently used. Evict the page used least often. This method requires tracking access count for each page. Some other techniques such as MFU, most frequently used, LIFO, last in first out, and second chance. Now here we see the example how virtual memory works. Imagine you are running a large video editing application that requires 16 GB of memory, but your computer only has 8 GB of physical RAM. Without virtual memory, the application would not be able to run or it would crash immediately. Here, how virtual memory allows it to function. Application starts. When the video editor starts, the OS assigns it a larger virtual address such that 16 GB, only the critical part of the application, and the data is immediately using are loaded into physical RAM. Then, accessing data. As you edit, the application tries to access a section of a video file that resides in its virtual address space, but is not currently in physical RAM. Page fault occurs. The CPU memory management unit detects this access attempts and realizes the required page of memory is not in RAM. This triggers a page fault interrupt. OS intervention. The OS take over, it identifies where the required page is located on secondary storage, such that your SSD or hard drive. Page swap. If physical RAM is full, the OS must choose an existing page in RAM. Using a page replacement algorithm, which we had seen before, to swap out to disk to make room, then it load the requested page from disk into the newly freed RAM frame. Process resumes. Once the page is loaded and the page table is updated, the OS instructs the CPU to reattempt the memory access. This time the data is found in RAM and the video editing application continues seamlessly, albeit with a slight delay due to the specific page fault. This process allows the application to think it has 16 GB of contiguous memory, while the OS efficiently manages the limited physical RAM and disk space, give the illusion of more memory than it physically available. So conclusion, the power of abstraction. Memory abstraction. Virtual memory provide powerful abstraction. Efficient utilization. It enable efficient resource use and protection. Modern OS core. Essential for all modern operating system. And fourth one is constant evaluation. Continues to advance with new tech. Virtual memory remains a cornerstone of computing. It allows system to run complex software efficiently. This technology adapts with hardware and software progress. It will continue to drive innovation. Summary of virtual memory. So, virtual memory creates the illusion of a larger continuous memory space than physically available. It allows application to run even when their entire data set does not fit into the physical RAM. And the technique through which we implement virtual memory is demand paging. The operating system manages memory pages swiping between a RAM and disk as needed during a page fault. This abstraction enables efficient resources utilization, memory protection, and is fundamental to modern operating system. Virtual memory is a cornerstone technology that ensures system can efficiently handle complex software and continuously adopts with hardware and software advancement. So thank you so much for your attention. I appreciate you taking the time to learn about virtual memory and its critical role in modern computing. Your engagement and interest are highly valued. We hope this presentation provide a clear and comprehensive understanding of this fundamental technology. I share this PPT in description, so you can go through there. Thank you.